To continue, we have to Professor Ana Dubova introduce to Professor Mejdi Azaiez. You can start, Professor Ana.
Okay, thank you very much, Mejdi, for accepting the invitation to give a talk in our seminar. So I will present you to the audience. So Professor Mejdi Azaiez is a specialist in numerical analysis. His interest covers several areas, such as the approximation of partial differential equations by high-order method, inverse problems, constraint spectrum calculation, and model and data reduction method. Currently, he is a full professor at Polytechnic Institute of Bordeaux in France, and a researcher at the Institute of Mechanics and Engineering based at the University of Bordeaux. He has been as an invited professor in several universities, including École Polytechnique de Lausanne, Sevilla, and Xiamen University in China. He has been leading several academic and industrial projects. He has been the head of the Department of Mechanical Engineering, and now he head international relations area in his university. He served as a scientific expert member and the executive board member of several journals. So today he will give a talk about least square pressure recovery in random reduced order method for incompressible flows. So please, you can start.
Okay, thank you, Anna, for this nice and generous presentation. And I am happy to participate to this seminar. And I must confess that I completely missed the fact that we are changing hour. And I was thinking that I am starting 1 hour before, but it is in France now, it is 8. I was thinking it is 7. Okay, this is to situate the situation and to say why it was like hurry. Anyway, I am really happy to present this subject because it is one of the results we obtained thanks to very, let's say, important and long collaboration with the University of Sevilla, and especially with the team of Thomas Chacon and with his group. And this work was achieved with the participation of Isabel Sanchez, Murad from University Sorbonne, and of course, once again, Thomas Chacon. The keywords are to work in the framework of model reduction, let's say reduced order method, and to try to answer to one question. The question is how to compute pressure. Okay, I will rapidly say a few words about the motivation. I will present the idea and I will give some numerical results, and I will pass sometimes to convince you with some numerical tests. Okay, so the motivation, I would say that I am dealing with an incompressible flow. Incompressible flow means that you are looking for a velocity u with the constraint that divergence u is equal 0. And one can imagine several possibilities to derive this kind of velocity. And one of them is to add a Lagrangian multiplier that we call pressure. And this pressure is here to balance the constraint divergence u equals 0. And I mean, if your velocity is already divergence free, it's clear that there is no way, at least with a natural way, to compute the pressure. The pressure, there's the correlation between pressure and constraint, okay? And when you are dealing with model reduction, let me say a few words about the spirit of it. Model reduction, it means that you have your initial model, you run the model, you compute, and let's say that you compute it for instance, if you are looking for time-space dependent problem, you mean that you are computing with time and you record, you record what you call snapshots. I mean, you register all this data that represent the solution in each time. And once you have this data, you have to create a reduced basis. This basis is supposed to be cardinal, to be dimension much less than the initial data. And of course, if you run a solver to compute a solution, for instance, for Navier-Stokes equation with divergence free, all your velocity are divergence free. So I mean, if you want to create a reduced basis, this reduced basis will come from the initial data. And once again, let me repeat that this data already satisfies divergence free. So it means that with this data, I'm able to create a reduced basis, but when I'm going to solve my Navier-Stokes in this reduced basis, it's clear that everything I will compute will be divergence free. So how to recover the pressure? This is one of the questions that we need to solve when we deal with the reduced order method. Several other questions also remains open, like nonlinearity, like long time computation, like multiparameter. But let's focus on one easy, difficult, but easy to present as a question. Today, we have two directions that I'm going to present here, what we call Poisson pressure equations, and momentum equation recovery, what we call PPA and MEQ. Okay, so if I look for the natural idea, suppose that you already compute the velocity, so you are able to produce the right-hand side of this equation, and mean that your gradient P that you want to solve, it is equal to some kind of difference between the source and the advection diffusion quantity. So once you want to compute this, maybe it's natural to say, okay, I will put the divergence and I will try to work to find a good idea of producing a boundary condition. Let me give two remarks. The first remark that if you look for this problem, which is one idea, natural idea to give an operator to solve, to produce, and to recover the pressure, it's clear that the pressure here needs more regularity than the initial pressure of Navier-Stokes. Remember that Navier-Stokes, the pressure is supposed to be L2. And here, if you want to solve this problem, we go with the hypothesis that P is H1. So you are making some kind of putting distance between the initial requirement and the new way to recover the pressure. The other point is the boundary condition. It is written in red. We need boundary conditions, so we try to find some. I think I can mention the last work done by Thomas Chacon and his group. They produced what I can consider as the best boundary condition between codes. I mean, this is coming from the maximum information that they can put. And the idea is to handle the problem with the weak formulation and to make implicit the boundary condition. So this is, let's say, the state of the art very rapidly about what we can found in the literature. This is another way that people from reduced model, they propose. You can read with me this equation. I mean, the idea is, okay, I am looking for the reduced pressure, and the reduced pressure will be in the reduced space. And instead of solving gradient PR, I will look at the weak formulation, and I have to work, of course, dear colleagues, if I consider the velocity as a velocity coming from the reduced space, that it will not work because the divergence is free. So the idea is to enrich the space of the velocity. Remember that I have one set of velocity that I'm going to compute from the reduced basis, which is divergence free, and I have to add some, let's say, Lagrangian multiplier, but not for the divergence free, from the rotational equal 0. So at the end, my problem I have to solve will look like this quantity. And the idea now is to work on how to propose this space that I'm going to add to enrich the reduced velocity divergence free space. Okay, so this is a reminder. I mean, once we do this, there is one idea that proposed by Patira and Gianluigi and many other colleagues. And the idea is, if I want to create velocity to enrich the space of the velocity to produce the pressure, I need to propose something which has to be stable in the sense of Mejdi LBB condition. I mean, and one way is to work on this equation that I show here. And in this case, if I am able to solve for giving some velocity respecting this equation, I am sure to produce an enrichment of the velocity to compute the pressure, reduce the pressure, and I am sure that also to produce something stable. This is what we can find in the literature. Let me go now with what we are proposing. What we are proposing comes from, I need at least to introduce a gradient operator, and the gradient operator is presented in the weak sense. So as you can see, I will respect the regularity of the initial problem. So a gradient QH, it's defined by its dual weak formulation. And note that, I mean, if I go with something with the regularity h-1, I can also introduce the Ritz representation. Ritz representation, I will offer a couple of it. One coming from K notation K equals 0, K equal 1 is related to the way to represent to produce the Ritz presentation. I mean, Ritz presentation with K equal 1, it's something in gradient. K equal 0, it is L2 classic 1. And if it's possible to keep this in mind, it will be very useful for the continuity of the talk. Okay, so now once we do this, the idea comes naturally. Think that I already compute the velocity. So I denote by TU the distance between the right-hand side of Navier-Stokes problem and the advection diffusion problem applied to my reduced velocity. This quantity is not zero. It is represented by TU, and I will look for the problem, how to minimize this functional. And I can minimize it with this norm, which is an x prime h. And x prime h is computed via the Ritz representation, and you can see immediately that I'm going to conduct my presentation with two possibilities, something with representation L2 and something with representation H1. So once I do this, the rest is some kind of computation. I mean, I have my first remark that PHK can be seen as a supermiser, and the only thing that I'm adding is that the fact that here my supermiser can cover also K equals 0 and K equal 1. K equal 1 is the previous one proposed by Patira and the papers that I mentioned before. Okay, so if you want to minimize this, you can prove that the normal equation will be the following one. And I think that I am looking for PR. I already have UR, and I have to solve this. And in my mind, I conduct the question by looking for the end is K equals 0 or equal 1. And this is written in the dimension, in the reduced space MR. The MR is the reduced space for the pressure. Okay, though this is something that can be done on offline. And if you want to look for the algebraic point of view of the story, think that I am already computing the space XH. H notation H is for the full model. It's, for instance, for example, for our case, it is finite element. And R is reduced space. And in one case, I have the basis coming from MR that I computed thanks to the snapshot and using SVD or PUD or equivalent. And the idea is to write the algebraic problem to recover the pressure, and which is, at the end, equivalent to solve an algebraic system. I can represent it like it is written by equation 4. And in this equation, we have in one side, I have this matrix, which is the representation of the gradient, but made with a weak way. This is B. And I have this mass matrix that can be computed in L2 on H1. And R is the right-hand side that represents the residue, some kind of residue, the distance between the right-hand side and the advection diffusion contribution once applied to UR. So at the end, this is very, very, very interesting because you can see that B, it is have the dimension of NR and H. And H is huge. NR is usually about 5, 6, 7, 10 maximum. And this in between operator, it is big one. But if you look for the global matrix, this matrix is with size NR and R. So it means that it is small. And also, this can be done on offline too. So if I can also explain this question of our approach to recover, this can be represented also by the point of view of supervisor. It means that, okay, you already fabricate XR, okay, and MR. And the idea now is to, X0R, it's the reduced space containing divergence-free velocity. And MR is the reduced basis computed from the snapshot of the pressure. And you ask yourself that you have to enrich, so you have to add this quantity. And this quantity is the gradient with the rates per representation. And it means that this is something that it will be inside XH, but with small dimension, and X0R is divergent. This is absolutely some kind of direct sum of two subspaces of XH, one containing divergence-free velocity, and the other one is the gradient of function, and the gradient has to be represented by L2 or H1 rate representation. I would say that K equal 1, it is something that we can find also in the literature, but not given and explain it as we are doing right now. But another way, but K equals 0, it's absolutely new. So we can also continue the discussion to say that at the end, once I want to solve the problem with the reduced basis, I can split it directly in two steps. The first one, I will solve my reduced velocity. I compute the right-hand side, and I have to solve the pressure, or reduced pressure. So it means that something that can be done, not completely in parallel, because I want to do this. I need this for the second equation, but I mean, I split completely the solution of UR from PR. Okay, as it is written, the conclusion, the pressure obtained by supervisor is the one obtained by the last square procedure. And once again, I would like to add that here we open the door of supervisor procedure to another type of construction of supervisor, which correspond to K equals 0. Okay, look, error estimates. This is something fundamental to appreciate what we are proposing. I'm not going to develop the mathematics behind this, but I would just want to share the result. Okay, fixing the notation, pH is the pressure that you already compute using finite element. This is what you call the data, reliable data, the data coming from your favorite simulator. It can be finite element, finite spectral method. For instance, here it's finite element. PR is the pressure that we computed thanks to our procedure. We can prove that the error that we commit, what you obtain, the distance between what we are computed with the full model and with the reduced model is bounded by two quantities. One is the distance between pH and your reduced space. I mean, roughly speaking, this means that, for example, if you are using SVD, you construct the reduced space of the pressure by keeping the first modes. This quantity that I present here will be computing given by the information coming from all the eigenvalue that I am neglecting. I mean, this is the Q of the series that I do not consider. I mean, if I take 4 and I let part of 100, the error will come from the 100. And this is on one side. The other side is, of course, the error coming from the quality of our resolution of the reduced velocity. This is mean that we have T the distance between the right-hand side and the finite element solution, and the distance between the right-hand side and the reducer. This is the quality of your resolution of the velocity using reduced model. I mean, I have to add the two sources of error, and this is something up to me, it's optimal. I mean, in the sense that I have a couple of sources of errors, and I have some of them to control the error between my finite element computer solution and the reduced solution. Okay, when k equals 0, this constant is something correspond to the inverse estimate. Okay, so this is likely for finite element, it is a constant, and for some other type of approximation, I'm thinking about spectral method. This can be something about that proportional to h1 over h squared. When k is equal to 1, this constant is independent of h. This is one side, and now I will fix another problem. This is Navier-Stokes problem. We have the nonlinear term. We have time-dependent problem. I consider directly boundary condition one side and open flow boundary condition. This is stress is equal to 0 and the Newman boundary condition. You understand that I will make my favorite time approximation here, implicit Euler. And this is not the key, but we need some approximation, so we took this. And for each time step, I am solving this problem with the bilinear form A that you know, and I am introducing this bilinear form that I apply on the pressure. And the right-hand side is the physical right-hand side plus time approximation. Okay, so this is the foam model. Okay, this is what you can find in your favorite finite element code. And this is the reduced model. I mean, I solve my velocity, and I could I recover the pressure using our technology. Our method. Okay, so this is some notation to represent the information, the data, velocity, pressure, reduced velocity, reduced pressure. This is classic notation. Okay, so if I consider the question of the error estimation for this problem, namely Navier-Stokes equation with what I presented before, once again, I see that for k equals 0, I have more accurate information about the error. It is given here. And if I consider k equal 1, I can see that I have the same quantity, distance between reduced space and full model space for the pressure, distance between UH and UR. This is in L2 H1. And for the k equal 1, I'm adding another source of error, which is the derivative in time between UH and UR. And it is given here. Now, this is something, this information is quite interesting. Okay. Let me now share with you some research. I see. Okay. Okay. I consider two. Okay, this is something quite technical, but I must be honest and share this information to understand better some numerical results. I mean, I will consider something that I call unconstrained last square method. This is correspond to solve the problem as I presented before. And, you know, when you construct your reduced basis, for our case, we are using SVD or POD, which means that we are producing a singular value and singular functions. And the operator are all symmetric, and our basis has to respect the information that the vector, function vector of basis are orthogonal, and the scalar product that we are considering to create the basis. And from the numerical point of view, this fundamental property is not ensured. We can rapidly see when I consider my basis and I make some numerical test to measure the scalar product, and rapidly after 5-6 modes, I lose this property, and this can be very negative for our approximation. That's why I'm proposing to keep this idea of this naive. I mean, I will run any code to produce this eigen and eigenfunction and eigenvalue. And I am adding another approach is to constrain. On one side, I will say that I'm going to solve the same question, but I will ask that amplitude of the modes has to be bounded. It has to be as well. And so I control with this quantity for G. This is the mode, and this is the eigenvalue. So I have to control at this. And finally, I will ensure that everything coming has to be orthogonal. This is given by 11. And this is F, it is Frobenius norm. Okay, so using 3, I will share with you 2 cases, very classic for our community. I mean, this is what we call benchmark tests. The first one is flow past cylinder. This is an unsteady case. This is the condition that we can find in any paper to validate new idea. And if you want to, this is the condition of the full simulation. I mean, this is the high fidelity data that I'm going to use to produce my basis. There's some indication about the time step, about the number of finite element. And this is the solution in velocity in red and pressure in green, left and right. And this is something that we observe, and this snapshot computed for Reynolds equal 100. And once I have this snapshot, I produced my reduced basis, and I compute. I'm not going to produce error and velocity because the error and velocity is not new. We have the same quality than any other method. But what can be interesting to share is the pressure, and let me help you to read these results. The first here, top left here, I am giving the value of the eigen value. These values are presented in sumilog, and we can see that we have decreasing exponentially to 0. This is good news. That means that the model can be reduced. And at the right-hand side, I mean here, I am using several methods. The green one, it is not using the method of momentum. I mean, I'm not reduced by looking for the minimum of the error or something as we did. No, we are just solving Laplacian. We are solving Laplacian with the best boundary condition that one can apply. This is red, which is the best behavior, correspond to reconstruction of the solution using the POD basis. Think that this is the best error that one can produce in the sense that it looks, I mean, it's like the error of interpolation. This is the best what one can do, okay? And blue, it is applying without, I mean, I consider the basis coming from our library without using method 1, method 2 to constrain and to correct the fact that we are losing the orthogonality. Blue, it's k equals 0. It means that supermiser with L2. This one is with H1. This is, I mean, what you can find in any method in literature. This is a new contribution. But if I apply the idea to ask that my modes, my solution will use modes with the control amplitude at left and even control of orthogonality at right, we can see that really an amazing result. I mean, let me focus on this one. You can see that, I mean, we have a nice behavior. There's no increasing of the error. And also we can see that we have a gain about 10 to 4. I mean, we go from red to blue. Blue is k equals 0, which is a new approach. K equal 1 is what some colleagues are using. And this is what we can naturally think to use, but it is to avoid. This is the ISO value. I mean, if you want to plot the error, this is the POD reconstruction. This is the best what can I do. We have an error of 10 to -7. And this is the method produced by Laplacian with the best boundary condition that we can offer. And this is k equals 0. And we can see that 10 to minus 7, 10 to minus 7, and 10 to minus 5, 10 to minus 6. Okay, the last cases concern the driving cavity, which is interesting because we have singularity in the corner. Okay, and we are Reynolds equal 10,000, and this is also a steady situation. And I repeat the exercise, and I can see that the idea of the eigenvalue coming from the POD approximation is decreasing exponentially. And let me go directly to this. And once again, if I see the blue, it looks like really as optimal as the best approximation, which is the POD interpolation. And we are winning something very, very important between the classic Laplacian idea, the supermiser with H1 representation and L2 representation. This is really interesting. And then even when you compute the supermiser, I mean, solving the case k equals 0, it's something like we invert to mass matrix. Okay, this is the error, and I like this picture because I see that for k equals 0, we have absolutely the same shape, same behavior than the interpolation error. So this is absolutely what we can, what we wish to have when we are trying to approximate. I think that I am almost at the end. Maybe we, as usual, we have the conclusion, but we have many ideas of extension. And among all this, I will share with you one, and I need to go back. You see, I showed that every time k equals 0 is better, but k equals 0 and k equal 1, think that k equal 1, the theory said that we have another error coming from this. And the idea that we will test, I hope, as soon as possible, is once we will construct our snapshot, maybe we can think not to register or to record the velocity in each time step, but maybe the velocity and the derivative of the velocity. So if you consider before SVD or POD to go with some scalar product that contain or given, no, let's keep L2 scalar product, but just adding in the snapshot velocity, time derivative, velocity, time derivative, and maybe we have a hope to reconsider the error of estimation, and maybe we will win, and we will have good news, and we will make k equal 1 with special snapshot are as good as k equals 0 with classic snapshot. This is my last remark, and I know that I was very fast, but okay, this is, thank you for your attention, and I'll be happy to answer to your question, if any.
Okay, thank you very much for this wonderful talk. And also, in spite of the time you've been with us. So are there any questions from the audience? Please, you can use the microphone or also use the chat for your questions. Yeah, audio is open, so you can use it. I have just a curiosity. Okay, so if you compare the classical, for example, finite element method and the reduced order method with the time of computation, do you notice a lot of difference in the computations?
I don't have here some, let's say, indication because we focus on this contribution to really produce a good way to cover the pressure with no boundary condition, with a good regularity. I mean, good regularity. I mean, we keep the regularity of the initial problem. But I know that in many cases for really important simulation that the group of Thomas made and used to made with reduced model, we win. We are dividing by an important number by 100. I don't know if Thomas is here, but I think that this is the key. If you do not divide by big number, the CPU time is, we don't need to reduce the model. Okay.
Yeah.
Yeah. Really, I mean, the idea is to produce in the real time. I mean, on the solution, to be able to make it even with your computer and to have the solution immediately. Okay, so I can confirm that we win a lot of CPU time. This is not a question of dividing by 2 or 3. We divide by 10, by sometimes even 100. This is fundamental. I mean, once you finish to propose something to recover the pressure, you need to show that you are really winning time. Otherwise, the best model is the full model.
Yeah. Okay. So I don't know if there are other questions. So if not, we thank you again, and
thank you for the invitation, and sorry because it was quite rapid. Okay, thank you.
Thank
bye.
You bye.
Thank you, Anna. Thank you a lot, Professor Mejdi Azaiez, for
Thank you for your invitation. Hope next time.
excellent